All right, now, this is Mark. We're just chilling here, watching some Game of Life. Got to get a little relaxed in preparation for watching some point charge animations. So here's the Game of Life. Notice how a simple rule set determines where new cells pop into existence and when they die, how long they live. Over time, the whole situation evolves. Some forms can blink in and out forever, up and down, or in some other form, or in a moving form. And you never know what'll happen. Something could come through and destroy that form and generate something far more interesting, or cause everything to perish. But here you see now we've reached a steady state. It's just blinking, unless something comes in from the outside and perturbs the system. These are the structures. They're going to live on forever. When you think about point charge systems, they can move all over. They have a velocity. The point charges themselves can't be destroyed. They were always here and they're always going to be here. So we can follow the path of every point charge in the universe, no matter where it ends up. If it ends up in a proton or a neutron, electron, farther down into a quark, or if it ends up in a space-time assembly of point charges. And then no matter where it goes, is it deep in the Earth's core? Is it deep inside a star? Is it on the edge of a black hole or far inside a black hole? What are the kinds of structures that form at all these positions in the universe? And it's just like Conway's Game of Life. We're just going to look at it through the lens of point charges. But we're going to start with some simple cases to get our minds around this concept. I did make a video on the differential between Conway's Game of Life and the point charge theory of the universe. It's actually kind of fascinating because you've got, the cellular automata of Conway versus like a continuous geometry of Euclidean space and time in point charge theory. There are things that happen that are similar. Structure forms, assembly forms. Assemblies can be collided and form different assemblies or disassemble into parts to be used another time. So there's some very similar things that happen, and what's really interesting, I think, is that Conway's Game of Life has a very simple rule set, and I think nature does too. I think it's up to us to decipher the simple equations that govern nature. And away they go. In this experiment, we're starting with various numbers of point charges. We're indicating the electrino in blue as the negative point charge, and the positrino in red as the positive point charge. And we're releasing them all with a velocity of 0 in random positions to see what happens. And as you can see, look, we're already forming some kind of a structure here, and I'll play this one again so you can see how it evolves. We're going to start with 4 point charges, 2 of each, and we're going to depict the relationships with lines. Red to blue is a purple line, red to red is a red line, and blue to blue is a blue line, which doesn't show up very well. And we're going to start these all with a velocity of 0, so no kinetic energy, and we're just going to see what happens. And we've got some physics programmed in here that is just kind of approximate physics, not even close really, just that knows about the concept of opposites attract and likes repel. So you can see this is starting out. I've got it tuned down to really slow motion. It just so happens that we have 3 point charges over on the right side, and 3 point charges over on the left side. And 3 point charges over on the right side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And 3 point charges over on the left side. And two neutrinos and one positrino. And you can see because they attract, they kind of get into this oscillating pattern. Meanwhile, there's this other positrino way off to the left that's kind of hanging out and going, hey, what are you guys doing over there? And as it exerts more influence, it changes the geometry of the oscillation of the 3-point charges on the right. And you can see the one on the left is kind of going, I'm coming over, what's happening? And again, like the geometry is getting quite interesting on the right side of the diagram. So now we've got to the point where we kind of have these two on the right that are orbiting each other, and we have the one electrino up near the top that's kind of just hanging out, and the positrino is still approaching. And now, as it continues to evolve, the question really is, will it form an assembly, or will it just, kind of dissipate to infinity or to just some random configuration over time? But now we're starting to see that while it is an overall assembly, there's also two sub-assemblies right now. There's a pair on the right that is forming a binary and a pair on the left that is starting to form a binary. And they're still not really kind of sure, like, is this stable? How are we going to get long term? What's the pattern? Who's orbiting who? Which way are you orbiting? Which way should I be orbiting? But this is all just part of the actual action and how the kinetic and potential energies settle down among these 4-point charges. And now as we speed back up, we seem to have formed some kind of long-term semi-stable assembly with two sub-assemblies, each orbiting in a circular pattern, looks like clockwise. This is fascinating. And they're off. I like to run these simulations multiple times because sometimes you'll see a new behavior that you didn't see in the previous simulation. I've added a scale for the time speed in the upper left because we'll see some things at different speeds here. Here you see, this is kind of interesting. We've got a tight binary on the right and a wide binary on the left. And kind of looks like it's stable there almost. But uh, if you're carefully looking, you see notice they are kind of drawing together. So even though it's been living for a long time in this semi-stable configuration, there's still something higher level happening that's pulling them together. Uh-oh, I've slowed it down. Now you see, oh my gosh, then what's happened? We've had like some kind of an interaction. Let's go backwards. Now we're going at minus 2t in the scale backwards to see what happened. Oh my gosh, what was that? So when we get reversed here, you want to like pay attention to like maybe, I don't know, I can only look at one particle at a time, but pick one to pay attention to, like the red on the left, and watch it all the way through, or the blue on the left, watch it all the way through. If you could do two of them, do both of those and see what happens at the end. Where do they end up? So here we got the red on the left and the blue on the left are still on the left, and they're still in a binary. But now we have, whoa, they just like the red on the left is now the red on the right. I'm kind of lost where the blue was from because I'm too slow to watch multiple ones at the same time. But now the red that was on the left is the red on the right. What do these semi-stable states mean? Why do they last as long as they do? And what causes the overall assembly to change from one shape or geometry to another? And away they go. I just wanted to show this quickly to illustrate that it is possible to get counter-rotating binaries. This simulation goes on for another minute like this, which is quite interesting. And they're off. Now we have 6-point charges. Turns out this simulation is relatively stable for the full minute that I ran it for. It's interesting because we have three binaries in this system with 6-point charges, and they each seem to have different orbital radii and orbital frequency, which is kind of fascinating because it seems stable. You would think, you know, why did it pick these particular frequencies? What are the interactions? But just as a reminder, the blue lines are relationships between two neutrinos, red lines are between two positrinos, and purple lines are relationships between the opposites, electrino and positrino. And I haven't built in the delays yet from path history. This clip is interesting because there's a number of geometry changes from what look like semi-stable intermediate stages. So what's happening here? What exactly is going on in the dynamical geometry of these point charges in this set of physics? And we have 8 point charges out of the starting gate. What we see here is an evolving dynamical geometry, and the math would be incredible to understand why it evolves to these different states. Of course, I'm using some bogus physics here, that's just a basic approximation. But as we get towards the actual physics, it would be fascinating to understand this. Now I recommend putting me on mute and watching this again on slow motion. All right, now, the big question here is whether the two middle binaries can manage to rotate 180 degrees clockwise. Let's watch. Why did this behavior emerge? Let's simulate 10-point charges now. 5 electrinos, 5 positrinos. Again, we're forming binaries, but we're also having reactions along the way. I've got several clips here in a row. Let's just sit back and see what emerges. Now we're coming at you with multiple simulations from 12 to 22 point charges. 50% positrino, 50% electrino in each case. Sit back and enjoy, put on some good music, and talk to you next time.